is going to be another one-take video and go through a few more of these examples. Maybe a few pauses if I need to double check something, but otherwise, if there are mistakes, we'll try to fix them along the way. We're going to look at this example. Sometimes I've taken the squared away. I think I'm going to leave it as it is. I may have mentioned, or in your version of the note packet, it may be missing, or I may have mentioned I was going to take it away, but I'm just going to go ahead and work through it as given. And in that case, we're going to have degree 4 over degree 5. And so we can go ahead and start our partial fractions. In this case, we've got that repeated factor, and that's one of the reasons I want to leave this one. So we're going to have just a single x term, but then we need a term for x squared plus 1 to the first power, just leave off the parentheses, and then a term for x squared plus 1 to the second. We're going to have a here, degree 1 less. Since this is an irreducible quadratic, we'll get bx plus c. And then keep in mind that when you have the repeated factor, it's still just based on the factor, what you put up in the numerator. So dx plus e here. And then we'll clear everything out, multiply through by that denominator. And so we're going to end up with x to the 4th plus 1 equals a times x squared plus 1 quantity squared plus bx plus c times, we'll have the x, and then one of these x squared plus 1 factors, again we're multiplying through by this denominator, so one of these will cancel, but the other one will remain. And our last term is going to be that dx plus e times x. And we could start plugging in values. We have 1, 2, 3, 4, 5 unknowns, so I need to plug in 5 values of x. I think in this case I'm going to just expand and compare coefficients. I'm still going to have 5 equations that I have to solve for, but I think overall that's going to be easier. I'm going to go ahead and leave myself some more room for that. X to the 4th, and then you don't have to write these down, but keep in mind that we have coefficients of 0 on our x cubed and x squared and x to the 1st terms. So we'll need to set any x cubed, x squared, x to the 1st coefficients equal to 0. When we expand this out, this is going to look like x to the 4th plus 2x squared plus 1, and then multiply that through by a. I'm going to go ahead and, before I do any grouping, we'll just write everything down. You don't have to do it that way. You can start putting in some placeholders for all these different powers of x and fill them in where they go, but already kind of locked in here. This is going to be x cubed plus x, and then multiply that through by bx plus c. So we'll have a b x to the 4th, b x squared, and then c x cubed and c times x. And then with this last term, dx squared plus e times x. And then when we go through and group the terms, we're actually going to end up with equations that are fairly straightforward. We'll have a and b times x to the 4th, so a plus b, x to the 4th. Our x cubed terms here are, well, I guess just c. Just go ahead and write that down without the parentheses. Our x squared terms are the 2a that we have here, b, and then we've got this dx squared. And that's x squared. Our x terms, we've got c and e. Right here and right here. And then just constant of a. So some of these values we're going to be able to solve for pretty quickly. This is going to be a very easy system to work with. Looking at the x to the 4th terms, a plus b has to be equal to 1. C is equal to 0. 2a plus b plus d, that's going to be equal to 0. C plus e is equal to 0, and a, well, a is equal to 1. And so we get, let's just go ahead and write these down, but we're going to get a lot of these values directly. Again, a plus b is equal to 1, and, well, I'll just write them down in the order that I described them here, but we already know that c is equal to 0. We'll be able to substitute that in that fourth equation. This is equal to 0. C plus e is equal to 0, and then a is equal to 1. Equals 1. And because of the a being equal to 1 and the c being equal to 0, that means that this turns into 0 plus e equals 0, so e equals 0. And we know that c is equal to 0. This turns into a, which is 1 plus b equal to 1. So that means that b is equal to 0. A lot of these terms are going to drop out. And then 2a plus b plus c is equal to 0. And at that point, we're going to have 2. Oh, that should have been a d. I was going to say, I think I'm missing something here. That wouldn't have made sense. This is a d. So that turns into 2 plus 0 plus d equals 0, which means that d is negative 2. So then we can come back and start putting these values in. A is 1, b is 0, so that's going to drop out. C is 0, so this term is going to go away completely, actually. D is negative 2, and e is equal to 0. That one's right here. So that means that our integral simplifies quite a bit. We're going to get 1 over x, we know how to integrate that, plus negative 2x, I guess I can put the negative out front, over x squared plus 1 squared dx. I'm going to move this negative out in front of that term. And we'll get natural log of the absolute value of x from here. And in this one, we're going to let u be equal to x squared plus 1. du is equal to 2x dx. And so that u substitution is going to lead us to 1 over u squared du, ignoring the negative for now. So we're going to end up with negative 1 over u. So I'm going to put that into the final answer here, natural log absolute value of x minus 1 over x squared plus 1, and then a plus c to cover everything. And that's our final answer. We can double check in Mathematica and see if the partial fraction decomposition was correct. Probably should have done that before. Go ahead and run that now, and we see that it does agree with what we got. Looking at the instance where we don't have power of 2 on that, we would need long division in that case, and it looks like we get a quotient of x. And then our other values, we wouldn't have as many unknowns because we don't have the repeated factor. So we just get a over x and then bx plus c over the 1 plus x squared. But it looks like we have some similar values that would show up there. So long division step would take a little bit longer, but then our partial fraction process after that would be quite a bit shorter. Let's look at this next example, x minus 1 over x squared plus 3x plus 2. I want to be careful and make sure that things are reduced if they can be. So the x squared, if we put that into, or this denominator, let's put that into our quadratic equation. And really you just need to look at that discriminant, the b squared minus 4ac that's going to be under the square root. That's going to end up determining whether we have any real roots or not. If this quantity is negative, then we know that it's irreducible. Does this one factor? Doesn't look like this one's going to factor nicely, but our b value of 9 minus 4 times a times c which is 1 and 2. So we are going to get 1 underneath the square root. So this will have roots, and no, I guess that one does factor nicely. If you saw that more quickly than I did, if we didn't realize what they were, we could go through the quadratic equation. For any of these, if you're having to do factoring yourself, then they're probably set up to factor pretty nicely, just because we don't want to spend too much time on that part of the process. But this is going to look like x plus 2 and x plus 1. And if I had recognized that at the beginning, I wouldn't have bothered doing this check. If I know that I can factor it, then just go ahead and factor. So we're going to do our partial fraction decomposition, x minus 1 over this. In this case, we could probably even jump past this step. It's going to be a fairly straightforward one. We've just got the two linear factors and no repeated roots. So just a over x plus 2 plus b over x plus 1. And that means that x is equal to a times x plus 1 plus b times x minus 2. Whether we decide to plug in values of x or expand, either way, this is going to be a pretty quick one to solve for a and b. But since we can plug in x equals -1 and x equals 2, I'm just going to go ahead and do that. That'll be pretty fast. -1 is going to be equal to, this a term will drop out, and then we'll have b times x minus 2, which will be -3. So that means that b is equal to 1/3 once we divide and cancel the negatives. Plug in x equals 2. That's going to give us 2 on this side. The b term is going to drop out. This is going to be a times 3. So that means that a is equal to 2/3. And our integral, I'm just going to bring this down here, is equal to, plugging in our values there, we're going to get, I'm just going to write it like this, 2/3 times 1 over x plus 2 plus 1/3 times 1 over x plus 1. Both of those are going to have natural log in the answer. This will be 2/3 natural log of the absolute value of x plus 2 plus 1/3 natural log of the absolute value of x plus 1 plus c. I guess if you wanted to bring these coefficients inside as exponents and then combine the natural logs, you could do that, but there's no particular reason that you have to go about it that way. The next one is going to be similar, although it's already factored for us, so we can jump right into the partial fraction process. I'm going to leave myself some space here for the result of that and just bring the partial fractions over here. I should move that up a little bit more. It is what it is. X minus 9 over, probably going to want a little bit more room, and I'm not going to need as much as I have there. X minus 9 over x plus 5, x minus 2. We're going to have a over x plus 5 plus b over x minus 2. Go ahead and multiply through by our denominator to clear things out. X minus 9 is going to be equal to a times x minus 2 plus b times x plus 5. And once again, I have the choice of either expanding and comparing or plugging in values, but since I can plug in 2 and plug in -5 and get to a and b right away, I'm just going to take that approach. That's going to be faster here. That's going to give us -7 on this side. This term is going to drop out, and then we're going to have b times 7. So b is equal to -1, and then we're going to plug in x equals -5. That'll give us -14 on that side, and that's going to be equal to a times -7 plus 0. So that means that a is equal to 2. And then put those values in here, put that form into our integral. We'll have 2 over x plus 5 minus 1 over x minus 2. And then that's going to be equal to 2 times natural log the absolute value of x plus 5 minus natural log the absolute value of x minus 2 plus c. Again, if you wanted to use log properties and start bringing all that together, you could, but there's no particular reason that you have to unless there's a reason to bring it in. And then in this last example, we're going to do some factoring first to make sure we've got it factored as much as possible. This looks like the integral of, maybe I'll just focus on the non-integral portion first, since we're going to do partial fractions on it anyway. This, taking the x squared out, is going to leave us with x squared times x squared minus 1, but then that x squared minus 1 also factors into x plus 1 times x minus 1. So we need to get it into that form first. And then when you're dealing with x raised to a power, it's sometimes tempting to forget that there's a multiplicity there, but I do need to treat that as 2 factors of x. So I'm going to set this equal to, I'm going to have an a over x term, and then I'm going to have an x to the second term, and I'm just going to have b in the numerator because this is the repeated, or this is the multiplicity corresponding to that. But the factor itself is still x, so I'm still going to have just a constant, a degree 1 less here than the degree of the factor. And if it helps, we'll put parentheses around that if we want to emphasize that point. May be helpful to think of it that way. And then we'll have a term for the, I'm going to run out of space here. I'm going to have a term for the x plus 1 denominator factor and another for the x minus 1. Both of those are linear, so we'll just have a constant in the numerator. And that's going to turn into, when we clear out all of our denominators, we're going to get 1 equals multiplying through by a, so I'm going to have a times x plus 1 times x minus 1 plus b times x plus 1 times x minus 1, c times x squared times x minus 1, and then finally d times, and these are all added, d times x squared times x plus 1, because again these factors down here will cancel out. Because we had the repeated root of x, I'm going to have to go a little bit beyond just the 3 nice values that we could plug in. I'm going to need at least a 4th value here, but we've got 0, -1, and 1 are going to make a lot of these cancel out. So we'll go ahead and plug those in, and then we'll plug in one more value. I'm probably going to choose x equals 2. That should be reasonably nice to plug in. But I want to do that after I've gone through 0, 1, and -1, because that should allow me to solve for at least a couple of these. So plugging in x equals 0, we'll get 1 on the left-hand side, and that's going to be equal to, this term will drop out, this b term is going to stay, so I'll have b times 1 times -1, which will just be negative b. You could go ahead and write it down like that if you wanted to. This term's going to drop out, and this term's going to drop out. And so we end up with b equal to -1 once we divide through there. And then I can go ahead and put that in wherever I see those b's. We're going to plug in, I'm going to run out of space here, plug in x equals -1. Just do that one next since I'm looking at this factor here. I'm just going to get 1 on the left-hand side. This term is going to drop out. The b term is going to drop out. The c term is going to remain. I'll give a c times -1 squared times -2, and then the d term drops out. So that gives us our value of c, and well, this be -2c, divide that, so -1/2 for c. Not quite as nice, but let's still deal with that. I'm going to plug in x equals 1. And I'm still going to have just the constant on that side. The a term is going to drop out. The b term is going to drop out. The c term is going to drop out. The d term is going to remain. We'll get d times 1 times 2. So that means that d is equal to positive 1/2. And we can make that replacement. And I need one last value. I said I was probably going to plug in x equals 2. That'll allow me to solve for a, now that I know these constants. And given that I have this 1/2 here and over here, that makes me even more inclined. I'm just going to put this down here to plug in x equals 2. Should get some cancellations with the 1/2s that we're seeing there. So 1 is equal to a times 2 times 3 times 1, just going through each of those factors. And then this will be minus 1 times 3 times 1, plugging into here. And again, that negative coming from the b being equal to -1. And then plus 1/2 times 4 times 1. I guess that'll be a minus since c was -1/2. So let's change that. And then d is positive 1/2 times 4 times 3 here. And I'm still running out of space for these constants. Let's see how much I can fit down in here. So that gives me 1 is equal to 6a minus 3. What's this? Minus 2. And then this will be plus 6. Which means that 6a plus 1 is equal to 1. And that's nice because then a is equal to 0. So that term's going to drop out. Let me just confirm with our apart command. I haven't shown that on the others, but let's just look at that and make sure that's what we're getting. That looks correct. We don't have any 1/x terms in there. We see that we've got our b value of -1 showing up here. Our c value of -1/2, there's our negative, here's our 1/2 here and here, and then our d of 1/2. So then we're going to integrate that. That means our integral turns into -1/x². Try to make that a little bit neater. -1/x² minus 1/2 times 1/x plus 1 plus 1/2 over, or times 1/1 minus x minus 1. 1/2 times 1/x minus 1. And then integrate each of these. This will be an x to the -2, which turns into -1 x to the, x to the -2. Integrate that. X to the -1 divided by -1. We'll get a cancellation there, so that just ends up being 1/x. In the end, minus 1/2 natural log of the absolute value of x plus 1, and then plus 1/2 natural log absolute value of x minus 1, plus c to cover everything. And so that'll be our final answer. Again, you could use some log properties to put those natural log terms together, bring the 1/2 in as an exponent, combine those, but there's no reason that we have to do that. So that wraps up those examples. And I think those are all correct. I didn't check these other ones with the apart command. I guess I can run that real quick. You can pause it on screen if you want to see. Looks like we got the right things. That wasn't that one. That was the one that we had up here. And x plus 2, x plus 1. I think those values are... maybe I did that one. So there may have been a mistake there. I should have checked that along the way. This one, I think we may have... Did I check that? No, but that one looks okay. I'm going to pause the video and try to go back and find the mistake. You may already see what I did wrong here. I'm guessing it's just something with one of these values, but let me pause and correct that before we wrap things up. Okay, well, you were probably yelling at the screen the whole time. There were multiple mistakes in this one. There should have been an x minus 1 here, and there should have been a plus 2. So that's going to change things, although it does make it, well, I guess I'll make our numbers a little bit better. So this will end up being a -1 minus 1. I'm just going to fill that in there. And that turns this into 1. Which gives us a much nicer b-value of -2. And let's just double check, make sure that's what, yeah, that's what Mathematica was saying on that. And then on this side, if I'm plugging in x equals 2, this will be a 2 minus 1. Yes, 2 minus 1 there. And nope, it should be -2. So that will also change things. So plugging in x equals -2, because I was looking up here and not over here, plugging in x equals -2, we're going to end up with, what do we get now? -3. Just write out -2 minus 1, -3 on that. And then that will help things here. That's going to give us -1, and then that's 0. So there's the -3 divided by -1 gives us an a value of 3. So then I can fix that. I'm just going to erase these here. So our a value is 3. Yes, and our b value is -2. So that turns into 3 times natural log of the absolute value and -2 times that one. So that will now be our correct final answer. And at that point, I guess it would be even easier to bring these in, or slightly nicer. Not any easier, but I could bring these values in and, again, combine that into a single natural log if that was important to the process, which, again, it's not here.